Thank you. Cool. So the topic is Python 8 my homework. And what do I mean by that? Well, you might remember in university or high school, you may have done some maths assignments. And sometimes you'll do the maths assignment and you write out all the working out, etc. Sometimes you'll have a calculator that does it for you and it'll eat all of your working out. So I'm going to show you how you can use Python to solve that problem. Because traditionally, assignments like this are handwritten, and you'll see it can be quite messy. Like what is this thing here? I don't know. Neither will your lecturer or professor, and maybe you'll get marked down for it. Or you might like rewrite it with LaTeX, and LaTeX is great. It makes it very readable, but it's very tedious to write. It takes a lot of time. But even then, both of these are still not ideal, because even if you write everything up, you can't know for sure if it will be correct. And it might be messy. And even if it is correct, maybe you want to apply the same logic to the same question, but just with different parameters. And so I think we can do better with Jupyter and SymPy. And so I've made a little fake assignment here that I'm going to try and submit in 13 minutes. And with that keeping that in mind, I will cover some maths. Don't worry too much if you don't understand the maths. The main gist I want you to get out of this is how you can use Python and programming to help you out here. And so the first question I have is, show whether the following numbers can be represented as a sum of two squares. So we've got n is equal to a squared plus b squared. So as an example, 250 is 81 plus 169, and that's 9 squared plus 13 squared, so it's a sum of two squares. And we want to do that for 49, 85, and 343. And in my assignments, I'm very nice. I have a theory reminder there to tell you how to solve the problem. And I've written a positive integer n can be written as a sum of two squares if and only if there is no prime p that divides n an odd number of times for which p modulo 4 is equal to 3. That's confusing, but I will walk you through it and it will be fine. So I guess the first thing to keep in mind is that primes that divide n are also known as factors of n. And so the factors of 250 are 2, 5, 5, and 5, or 2 to the power of 1 and 5 to the power of 3. So what this basically says is that we want to check if there is any prime to the power of k such that p modulo 4 is equal to 3. So if we divide p by 4, we'll get 3 as a remainder, and where the power is odd, like this. And so really, this is just a program, right? And we can write some code to do that. So we just go through the factors of n, and we check that maths, and if there is something that follows that, then it is not a sum of two squares, and if that doesn't ever happen, then it is. Cool. So how do we calculate the factors? Well, most calculators that you'll use in university or high school have a factorization button. And sometimes you can do it in your head, but for really big numbers, maybe you can't. And I think that if the calculator has this button, so should I. So we're going to import one from SymPy. And we just do from SymPy import factor int, and then we run the code, and we'll get 2 has 2 to the power of 1 and 5 to the power of 3, and those are our factors. Awesome. So now we can take our code from before, and we've changed it around a bit. We've added in the factors using factor int. We're sorting them and getting them as items so we can iterate through it. And then those modulo statements that we had, I've just put them as variables so it's a bit easier to follow, and you'll see why later on. But now that we've done this, we can just print out the output for those 3 questions. And so we've got question 1 is true, 0.1 is true and 0.3 is false, which is great. We've basically solved our problem, but if I submit this, I don't think my lecturer will like it because it doesn't actually show that my working out. I mean, technically this is my working out, but maybe they won't accept that. So let's do better. And we can do that by just adding in some print statements. So now I've got a print statement here for printing out the factors, and then I've got some print statements for the like working out that we're doing. And then I've got some more print statements that are just like, yes, it is a sum of two squares, or no, it is not. And then we can run that, and you'll see we've got some more working out. So we've got the factors of 85, which showing what we're checking. Modulo 4 is equal to 1, so it's not equal to 3. 1 is odd, and so forth. And because none of those were true, we continue, and so forth. But again, I think we can do better, because this is just plain text. It's not really LaTeX that we had before, and maybe my lecturer doesn't understand code or plain text. Maybe you don't understand LaTeX. So what can we do? SymPy is actually really nice because it integrates really well with LaTeX. And what you can do is you can change some of your code to apply that. And so if we say visual equals true, now SymPy will output some LaTeX for us, which we can display with Jupyter. So in this case, we've got a much easier, it's no longer a dictionary, it's this pretty thing, so 2 to the power of 1, and so forth. And then what we can also do is we can import our equality statement. And what we'll do here is we just say, okay, 250 is equal to the factor of 250. What this will actually do, though, is it will just output true, because it's just actually doing equality checking. But what you can do is you can tell it, don't evaluate me what it is, and now you have a nice little equation that you can print out. And so the other thing we can do is import some markdown rendering. And what that lets us do is, along with displaying our equation, we can also change our print statements to display markdown. And now we can add a little bit of LaTeX in there for us as well. So the print statements that we've had before, we've massaged them a bit, made them a bit nicer. And then when we run this, we'll get something like this. And it's got 85 is equal to 17 and 5. And then we check those again. And then we've got some more maths that makes it a bit clearer. Awesome. So that kind of like gives you an idea of how you can display your maths using Python. But something that's a bit more powerful that we can do is actually do some calculations. And so I have this very long maths question that essentially you have a function, you put in some number of units, and then you get a profit. I'm not going to go into how explaining this. Do not worry about understanding this. If the talk was longer, we could. But essentially, it's a function that has a bunch of constant parameters that we can substitute in. And what we want to figure out is we want to find the maximal point. Like, what number of units do we want to produce to get the maximum profit? And we've also got our constants here. Cool. So how about we just like put this equation into Wolfram Alpha, right? What do we get then? And after you like replace all the constants with the numbers and then ask it for the maximum, you'll get this. So this will kind of help us visualize what we're doing. And you'll see it says the maximum profit you can get is like roughly 1 million. And it's when you sell these number of units, or like it's at this point. And you can see the point is here, and it's kind of on this surface. If you remember your simple calculus, you can imagine if we're looking at it on a 2D plane, we want to find the maximum of this curve. But in this case, we're looking at it on a 3D plane. Cool. But again, the problem is that Wolfram has told us the answer, which is great, but we can't actually submit that. And so what can we do instead? We can use SymPy to import some symbols. And so in this case, we've said we want the symbols U1, C0, and etc. And we've got our LaTeX things here. And we've also used those symbols to write out our equation programmatically. And we'll run that as well. And then we'll import a function. And what this basically lets us do is just display this equation as we had before, except we don't have to write any LaTeX. Then we can import, write out our constants. And then we want to do some maths. So in this case, I've written out the maximum value is where the gradient of f is equal to 0, where the gradient of f is we derive parts of the function. And essentially, we want to find what point will the gradient of f equal to 0. Again, don't worry too much, but we've got our matrix now, and we'll use our matrix to kind of stack our equations, so it kind of condenses it. And in the first case, we differentiate the function with respect to u1, and we've got this output here. And then in the second case, we differentiate it again with respect to u1, but we say don't evaluate it, so we can actually show the working out. And then in the second case, we differentiate it, but we do evaluate it. And now you see we have our differentiated equation. And then we can just say we want to make it equal to 0. Then SymPy will let us solve these equations for us. So we can say differentiate it with respect to u1, solve it with respect to u1. So basically it gets u1, puts it on one side. And then so that we can get our equation in a form where we can substitute all the variables, we want to substitute this into this part. So we only have it in terms of u2. And to do that, we use the substitute function. And you can see it's got this very long equation, and we want to find at what point it's equal to 0. To do that, we can, again, solve it with respect to u2 and find at what point, essentially it will rearrange it for us. And I think those kind of problems are kind of very basic anyway. So now we have the formula that we need to use, where if we substitute in all of our constants, we'll get the point at which it's maximal. And then if we do that, we've got it's at 7,000, like we saw before. So we can similarly do that for u1 or u1 star, but why would we copy and paste it all again and do it all over again when we can just reuse the existing code with the form of a function? So I have a function here that basically does everything we did before, with the main difference being that we have a for loop that replaces the constants and so forth. And then if we run that, you'll see we have all of the working out that we did before, but we also have it for u1, and now we have that point that is maximal. Cool. And then, if we want to get what the profit is, we take those 2 points, and we take the constants that we had before, and we just substitute it back into the equation, and now we have our maximal profit. Cool. So I think with this, you can take it and do a lot more with it, and I don't have enough time to cover more things. But the key thing that I want to say is that SymPy actually has a lot more power underneath this. And so that sum of squares that we talked about, it already has a function to calculate that. And you can just import that and use it as normal, along with a lot of other maths that you might already know. SymPy is also just built on a lot of maths, and people will it's just built on a lot of existing maths papers and formulas and et cetera and so forth. And the only way that it exists is by people reading that and translating it into code. And so if you're interested in this kind of field, you can go ahead and do that. Jupyter is also what I've been using to display this and so forth. And an important part actually is that we can just take all of this output and let's see, file, save and export as HTML. Save it here. And now our entire assignment that we had written out is now all in a HTML document, and we can just print that to a PDF or print that and submit it in paper or just submit it digitally. Awesome. And lastly, is a QR code and some links if you'd like to play around with the notebook yourself. But other than that, I want to thank my partner, my friends, and all of you for watching. And if you have any feedback, please let me know. I always love getting feedback, improving. Other than that, I think it's the end of the talk, and we have some time for questions.
Yeah. Does any question to Ethan? Yeah. So maybe next time we use this live hacking method for our homework or school life again. Yeah.
Thank you.
So very thanks, Ethan, your session. So we will have the next session on 10 minutes later. So thank you, Ethan, again.
Thank you very much.